to understand this solution, let's first observe that this term, v naught over omega naught sine of omega naught t, is going to be the same whatever the driving frequency of the external force might be. This doesn't depend on omega 1 at all. This is just going to be a steady sine function with an angular frequency of omega naught. This term here is going to be an amplitude, which we've already seen to be large when omega naught is close to omega 1 and small when omega naught and omega 1 are very different, multiplied by, of course, the factor 2, but more importantly by this sine of omega bar t, which is simply an oscillation with a frequency omega bar that's the average of the frequencies omega naught and omega 1, and also the sine of beta t, where beta is half the difference between omega naught and omega 1. So that when omega naught and omega 1 are close together, beta is going to be a small number, and omega bar is going to be very close to omega and omega 1. And now if beta is a small number, that's going to mean that the frequency with which this sine function varies is very long, and the frequency of this one is very close to the frequency of our driving frequency. Since omega naught and omega 1 are close together, they're both close to the driving frequency, so the average will be close to that frequency. Now let's look at all that in a little more detail. The thing that we need to understand is the sine of omega bar t times the sine of beta t. Now, we get a large beta if omega 1 is not close to omega naught, and we get a small value of beta if omega 1 is close to omega naught. Remember that beta is half the difference between omega naught and omega 1. It's given by the expression omega 1 minus omega naught over 2. Okay, omega bar is more or less close to omega naught, and I'm using omega 1 and omega 2. I need to make that an omega naught. It looks like a big blob now, but we understand what this means. Omega bar is just the average of omega 1 and omega naught. If beta is large, where omega 1 is not all that close to omega naught, then our natural frequency, or our average frequency omega bar is not going to be all that close to omega naught. That means that we're going to have a significant effect on the period of motion. We'll see what that means then when we combine these two effects. For a small beta, omega 1 is close to omega naught. This average is going to be close to the original frequency, to the natural frequency of the oscillator. And sine of omega bar t is going to be close to sine of omega naught t. To write that out more specifically, let's take the case where omega 1 is not close to omega naught. Okay? Then, in that case, as I've said, omega bar is not that close to omega 1 and omega naught, being halfway between these. If these aren't close together, halfway between them isn't all that close to either one. And in any case, the sine of omega bar t is just going to be a steady sine function with an angular frequency that's not all that close to omega naught in this case. Okay? Then the difference between these is going to be larger. If omega 1 and omega naught are not that close, beta is going to be fairly large. And what's that do to the sine of beta t? Well, that means that beta t will change by 2 pi more quickly. If beta is big, then t doesn't have to change that much to change the value of beta t by 2 pi. And every time the value of beta t changes by 2 pi, the value of the argument of the sine function changes by 2 pi, meaning that the sine function completes another cycle. So that if omega 1 is not close to omega naught, then beta is relatively large. Beta t changes fairly quickly, which means that the sine of beta t runs through its cycles with a high frequency. Now, what's that look like if we graph the sine of omega bar t and the sine of beta t? The sine of omega bar t has just some frequency. If these two are not close together, if they're close enough, then beta is going to be large enough to give the sine of beta t a much higher frequency. What happens in that case? Well, in that case, we have the sine of omega bar t running through its cycles, and we're multiplying this function by this function. Now, I've actually made the cycles a little bit longer here than they are here. I've made a half cycle. I haven't, excuse me, I haven't drawn this to the same scale that I drew this, apparently. These should be to the same scale, but I'm not going to change that right now. In any case, if we multiply these two functions, we're going to end up with something. Well, that wasn't. Okay. Let's draw that reflection there. So this will come down to here, this will come up to here. So we're going to have an overall frequency of omega bar, overall angular frequency of omega bar. This thing is going to oscillate at the same frequency as this function, but within that overall envelope, we're going to have rapid oscillations in the position according to this function. Furthermore, if omega 1 is not all that close to omega naught, then the coefficient, which would be, if we bring the 2 over here, it'll be 2f over m divided by omega naught squared by omega 1 minus omega 1 squared. Omega naught and omega 1 aren't that close, so that this denominator won't be that small, which will make this term okay. Not sure I said that right. Omega naught and omega 1 are fairly far apart, making this large, which makes this quotient smaller, which reduces the amplitude. So we're going to get a lower amplitude motion with a lot of short frequencies occurring, but the amplitude is going to increase, then decrease, then increase, then decrease, so that this motion would look something like this. Small amplitude, then larger amplitude, and larger amplitude, and larger amplitude, then smaller and smaller and smaller, corresponding to this part of the picture, and then pretty much repeating that, maybe with a reversal in the symmetry of the motion. On the other hand, if omega 1 is close to omega naught, then we have a situation as depicted here. Omega 1 close to omega naught means that omega bar is going to be close to omega 1 and omega naught, close to our natural frequency, because our driving frequency is close to our natural frequency. A small value of beta, which of course, remember, beta is just half the difference between these two frequencies. So beta is small means that it takes beta t a long time to change by 2 pi, which means that the sine of beta t is going to have a long period. And if the two are close enough together, that period will be much longer than the sine of omega bar t. And that's going to lead us to a function that looks like this, where it's the sine of beta t that provides the envelope within which the oscillations occur, and the oscillations occur at close to the natural frequency. In addition, the amplitude of these oscillations, or at least the amplitude of this envelope, the maximum amplitude that you see in these oscillations, is going to be larger because omega naught squared minus omega 1 squared is going to be a lot smaller if these two numbers are close together. I'll also point out, it was done over here and it's done here, that omega naught squared minus omega 1 squared is simply, if we take the product of omega bar and beta, the numerator is omega 1 plus omega naught times omega 1 minus omega naught. If we multiply these together, we get omega 1 squared minus omega naught squared. And of course then we get a denominator of 4. So that this denominator, omega naught squared minus omega 1 squared, is going to have a magnitude. I should put a magnitude on this and a magnitude on this. Going to have a magnitude 4 times omega bar beta. Again, if we just multiply these out, we see that what we get here is 1/4 of this, so that we have to multiply the product of these two by 4 in order to get this. And I've noted that here also, that this is going to be 4 times this. If we divide 2 of this by 4 times this, we get a 2 in the denominator, and it's simple algebra to depict this term. And I should go ahead and put absolute value signs down here as well. It would be worth your experimentation to take a simple pendulum and drive it at a frequency close to its natural frequency, but go just a little fast maybe. Well, it's difficult to do, take some coordination. Or to drive it at a frequency that's much greater than its natural frequency. In this case, omega 1 is the frequency, angular frequency of my oscillation with my hand, and omega naught is the natural frequency, which is somewhat slower than that. That's this situation. We don't get much amplitude in our oscillations, and they alternate: short, longer, 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 shorter, 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 and so forth. Whereas if we drive close to the natural frequency, we get something more like this.